So the second video, or well, the first video, the previous video, the vector one was the 0th video. So this is our first video, technically, in our Unit 3 work energy power discussion. We'll be doing a series on these. There'll probably be a work video, a work problems video, probably about 2 energy videos, practice energy video, work there'll be a conservation of energy video, work energy theorem video, and maybe some practice problems after that. So we're probably looking at somewhere around 6 or 7 total videos. But I'm probably going to get up to the conservation of energy done first, and then we'll go from there. So first video, work, energy, and power. Part number 1, work. We need to know what work is because it's a really important concept. It relates to energy, and it's just a really useful tool to know how to use. Here are learning targets. You know what work is, and you can calculate work. By the end of this video, you should be able to do all of those things. So in general, and I'll call this, start off, we'll say this is A. We'll talk about work. So for the first point that I want to make about work is that it's not really like this fancy thing. It's not a very nebulous thing like you might think, as in I go to work, I have a job, and when I'm at my job, I do work. When I come home, I'm not doing work, and maybe that person went to the plastic surgeon and had some work done. Energy can do work. Maybe electricity has work associated with it. All kinds of ways that we could use the word work. But almost all of them are incorrect for physics. When we talk about work in physics, we're talking about something very, 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 very specific. So physics work is a product, a dot product, in fact, and that's why I made the previous video, the first video, or the 0th video, to be the dot product discussion. But the work thing is a little bit more intense than just taking a dot product. So in general, I'm going to toss it right out here. Here's what we say the definition for work is. Work, W, is equal to the integral from A to B. So from position A to position B. Oftentimes A is an origin. Origin, sorry. Oftentimes A is an origin point, so it's a 0, or some other kind of 0. So origin or another kind of 0. So we do this integration from A to B, and most of you should be familiar with at least the basic idea of an integral, maybe not what it does or how to do it, but you know, it's a thing that exists in math. So we do this integration over this f vector dotted into dr vector. And so this thing here is called our element. The element of integration tells us what we're integrating. What is our integration? And maybe you think R. What is R? Is that a river? Is it a rectangle? Are we integrating over a rectangle? No, it is R as in a vector R. So if I have some path that my system goes over, and I have this is my origin, then I can point to any point on this path, and I can call this my R vector. So this would be like R2, maybe this is R1, this will be R3, R4, and of course this one would be R50. Just for the heck of it, why not? There could be 46 other R's in between R4 and R50. But it doesn't really matter what we call them. They're just some vector that points from an origin, A, to some final position, B. And when we do this integration, we're going to, or sorry, I shouldn't say that that's our origin is A and the point we're pointing to is B. Really, the origin is O, we call it O, and this right here is point A. And then I would do this integration all the way over here until I got to this point here, which is point B. I could do it the opposite direction too. There's always like an option to do that, but it would just flip the sign on, and it'd be the negative integral if we did it in that direction. That's not really important though, what this integration is and why we do it. I'm not going to really be super concerned about it, but this integral of force times dr, where dr is going to be a small chunk of distance, that's really what work is. So getting a little bit more into it, we'll talk about this idea of an integral or a path integral. So when I integrate from point A to point B, I can say maybe this is my origin, I'm pointing at point A, and then there's point B at the other end, and eventually I will end up there. But if I look at just a small slice of that, so from A to some tiny distance here, right? So this distance here, this difference between these two vectors, which I'll call maybe R1 and R2, is dr. It is d2 vector minus d1 vector. But in a sense, what it's doing is it's telling us integrate along this path. And this is what we would call a path integral. And it is really important that we understand that this is called a path integral, and this is just not regular integration. There's not much of a difference between integrating a path integral and regular integration, but it's a distinction that I want to make now, because when you go into multivariable calculus, or even maybe even Calc 2, you'll need to know what a path integral is and how to do it. Again, it's not much different when it comes to actually practicing doing these things. It's not much different from doing regular old integration. So our work is equal to force dotted into displacement integrated from A to B. And dr is our integration, so that's our dr, and we're going to integrate over that small little tiny piece, and then we're going to do our calculation, and then go to the next one, and then integrate over that next small little piece, and then calculate that, add it all together. That's what an integration is. But when we talked about the dot product, or when I talked about the dot product in the previous video, I said something about how if there is a force and it's dotted into a displacement, and the force is not parallel to the displacement, that dot product is zero. So one thing that we can take away from this work thing is that force that is parallel to displacement will do work. And kind of a addition, a little extra bit of that is that forces that are perpendicular, however you spell that word, perpendicular to displacement, will not do work. And just kind of a throwback to that video, if I have a force vector that is, say, 0, 1, and I have a displacement vector that is 1, 0, if I do that dot product, it says take 0 times 0, or 0 times 1, and then add that to 1 times 0, so I get 0 times 1 plus 1 times 0, and that's just 0. So if the force is not parallel to the displacement, as in if no part of that force is parallel to the displacement, it's entirely perpendicular, it will do no work. But if a force is not perfectly parallel, then it will still do work. So forces not entirely parallel to displacement can still do work. And the reason why they can do work is, well, let's look at a triangle. So here's my force vector, my overall force. Here is, and I'll do down below in blue, my displacement vector. And we know that this force is at some angle from the x-axis, and displacement is parallel to the x-axis. So this leg that I'm drawing in here of that vector, this is our, we'll call it f sub x vector. It's our x component of f. This will do work. But and I'll do it in red, this component, which we'll call fy vector, that component will do no work. However, this is worth mentioning, I guess, at this point. If this has a fixed axis that it can rotate around, that fy force will actually cause a torque. But that's, for another unit in the future. So you might say, okay, well, that fx, I know how to calculate fx. If I know force and I know theta, I can just say that's f times cosine theta. And that leads us to our next point. work is equal to force times distance times cosine theta. Why is that? Well, if I take my work formula, which says work is equal to the integral from a to b of f vector dotted into dr vector, then when I do that dot product, right, that's like saying take the x component and multiply it to the displacement, right? So in this triangle case that I've given you up here, take the x component of that force and multiply it as a scalar to the displacement. And when we do the dot product, what it does is it picks out that the portions that are parallel to each other. And so what I'd have is then an integral from a to b of fx times displacement times cosine theta. We'll just ignore with this integration for now, because all it's going to do is like change some stuff a tiny little bit, and we'll see how it changes it in a moment. But I want to point out the real important thing is that this is the same as saying f d cosine theta. Or maybe I should, sorry, I screwed up. F dotted into dr is going to be the integral from a to b of fx times drx plus fy times dry. And so these are two different integrals, right? And one of them is usually going to be 0. So let's say our motion is entirely in the x direction. That means dry is 0, and so that term goes away. And we get the integral of fx drx from a to b. But then that fx drx, we know what dr is entirely in the x direction, and so that would just be the integral from a to b, and our dr would just be, say, maybe dx, right? We've seen dx before. But fx, we have an equation for that, and that is f times cosine theta. In fact, let's change our limits of integration. We can always kind of do that in a lot of cases. And so I'm going to say we'll integrate from 0 to some distance d. And what my equation then becomes is the integral from 0 to d of f dx cosine theta. I do this integration, and I get I get f times x times cosine theta evaluated at 0 and d. So when my evaluation tells me plug in for x, d. And then also subtract from that f times 0 times cosine theta, where I plugged in my 0 limit for my x. My d limit goes down to here. So this second term, the negative term, is 0, and my result is f d cosine theta, which we said is work. So that's where that formula comes from, and this is really going to be the key thing that we will use to calculate work. We're not going to really do any dot products or anything like that. I'm not going to ask you to do any integration. All of this integration stuff I'm going to do for you, and it's going to be purely illustrative to show you and to justify why some things are the equations that we say they are, instead of just telling you, here's an equation. Because we tell you what an equation is in AP1. We tell you the equation for potential energy due to gravity is something in AP1. We tell it to you in honors or regular physics. In APC, though, we have to be able to mathematically justify every step that we take. Otherwise, we don't really have a good, sound reasoning for our answer. So, work is equal to FD cosine theta. If we look at that, then we can think about maybe the units of our work. We'll go to point F. The units of work, well, we can think about FD cosine theta. So we know the units of F, that's going to be a force, so its units are newtons. Units of distance or displacement, that's going to be meters. And then we have this cosine theta thing, which has no units. So cosine theta is a unitless thing. So my end result is that I get a force of newtons times a meter, and we call that a joule. Give it the capital letter J is our symbol. And also, a newton is a kilogram, right? It's mass times acceleration, so kilograms are mass. Acceleration is meter per second squared, so kilograms times meters over second squared. And then we multiply that by a meter, and what I get is a kilogram times meters squared over second squared, and that is also a joule. So if you represent it as a newton times a meter, or as a kilogram times a meter squared over second squared, that is correct. But please don't do that in your homework because it just makes me have to do extra work. Just call it a joule. Everybody will be happy and you won't have to write as much. So our formula is FD cosine theta to calculate work. Work is done by a force that's parallel to the displacement, and the units of work are joules. So let's look at an example of how to calculate this work stuff. Actually, we'll do this as 0.2. Example. So let's say that we have a force of 100 newtons, and we have a displacement d of 30 meters. So we're exerting this 100 Newton force constantly over a distance of 30 meters. And we'll say that the distance is in the x direction and the force is also horizontal, so in the x direction. And so when I do my FD cosine theta, I know that these are both, here's my force vector, here's my plus x direction, and there's my displacement vector, and the angle between my force and my displacement vector is 0. So I should have probably brought this up back with a few last page, but this angle theta here, this is not the angle of incline. If you have an inclined plane, this is not that theta. This angle here is the angle between the force and the displacement vector, like I drew in the previous slide where I had this triangle. This is theta. This is the theta we want. If I have an inclined plane, I'm pushing a mass up that inclined plane, and this is my force that I'm using, and my displacement is that my angle theta is 0, not this angle of incline. So when I do these problems, I'm going to call this angle, the angle of incline, I'm going to call it phi, the Greek letter phi, P-H-I. And this angle between F and D, I will call that theta. So here I can see that my angle or my forces are parallel to each other, so my angle is 0. Theta is 0 degrees, and that means I can calculate my force times distance times cosine theta, which is 0 degrees. Cosine of 0 is 1, and I get that my work done by this force is F times D, or 100 newtons times 30 meters, which gives me 3,000 newtons times meters, which we said was a joule. Do another example. Let's say that I have a force F vector, and it is 30 newtons in the x direction plus 0 newtons in the y direction. And we have a displacement vector, which is 10 meters. And we'll say 5 meters. 5 meters in the x direction plus 0 meters in the y direction. So I'll give you a second. Go ahead and pause the video, see if you can work out the answer to that, how much work is done by this force over that distance. Okay, should have had a chance to get that to work out. We can think of this as the dot product. We can think of it as F times D times cosine of theta. But if I look at this, when I think about is I have two vectors in the notation that is just perfect to do the dot product. So as it turns out, when we dot two vectors together, F dot D, it is equal to the magnitude of F times the magnitude of D times cosine of theta, the angle between those two vectors. This is also our work equation. Both of these are valid, and so I would probably do the, because I don't know the angle between these two things. I mean, sure, I can say it's 0 degrees for sure, because I know that they're both parallel to the x-axis. But just to be careful, let's do it in both methods. So my force vector dotted into my displacement vector, that's going to be 30 newtons in the x-hat plus 0 newtons in the y-hat, dotted into 5 meters in the x-hat plus 0 meters in the y-hat. So my dot product says multiply my x stuff together. That is 30 newtons times 5 meters, and then times x-hat dotted into x-hat, plus 0 newtons times 0 meters times y-hat dotted into y-hat. So x dot x and y dot y, those are both 1. I get 30 times 5 is 150. Newtons times meters is a joule, plus 0 times 0 is 0, y dot into y is 1, 1 times 0 is still 0, and so my result with the work done, 150 joules of work. For the other option, for FD cosine theta, I know that my angle theta is 0 degrees because they're both entirely in the x direction, and so I can say that my force is then just the magnitude of F, which is the square root of fx squared plus fy squared. And you don't have to do all this as long as you know that your magnitude here is going to be 30, but I'm just doing this to show you that indeed our magnitude using the Pythagorean theorem gives us 30 squared plus 0 squared in the square root, which is just the square root of 30 squared, or 30. So my displacement vector will have a similar option or a similar operation going on where I'd have the square root of 5 squared plus 0 squared, which is just 5. And so I take my force times my distance times cosine of the angle between them, theta. So force, again, is 30 newtons. Displacement magnitude is 5 meters. And then cosine of 0 degrees. Cosine of 0 is 1. 5 times 30 is 150 joules, and we get the same answer out. Awesome. So that's two different ways that you can calculate this stuff, but one of them, depending on what the notation you're given for your vector, one of them is going to be easier than the others. When it comes to actually doing problems for your homework and tests and things like that, and for the AP exam, you're just going to probably need to use FD cosine theta. Like 95% of the time, you'll use FD cosine theta. There might be a couple where they ask you to do an integral, but it's going to be such a simple integral, you shouldn't really have too much trouble with it. You'll just be using the power rule. All right. So we have force and distance, and we can calculate work if we know these two things. So let's think about some stuff. Let's think about, first of all, a spring. Or sorry, no, let's think about gravity first. We'll do 3. Gravity. So work done by gravity. And if you're going to pay attention to anything in this video, it's the next two examples, this one and the next one, because they're going to show you something that you'll see in the energy video that'll kind of justify why we do what we do in the energy video. So let's say I have a force of gravity, and or physical situation may be something like I have a ball. And the ball, I hold this ball out so it has 0 initial velocity, and then I drop it. So when I drop it, it's going to have the force of gravity acting down on it, and it will also move down. And so the angle between these two vectors is 0 degrees. So theta is 0 degrees. I also know there's an equation for my force of gravity that's going to be m times g times y hat, right? So that this tells us mass times gravity. That's the equation we're used to seeing for our force. And then this y hat gives it its vector quantity. It tells us it's pointed in the positive y direction, but I'm also going to say that down is the positive y direction for this problem because that's where all the motion is going to happen. And so it just kind of simplifies our calculations a little bit. All right, so to calculate the work done by gravity, we need to do the integral from 0 to y. So I'll say that this is y is equal to 0, and this is, so y initial is equal to 0, and y final is equal to y, just some value y. Could be 1 meter, could be 50 meters, could be a billion meters. Well, it can't be a billion meters. We'd have to use Newton's universal law of gravitation for that, but you get the idea. Just any numerical value that's close to the surface of Earth. My equation says take force and dot it into the displacement vector dr, and then integrate that. You do not need to do this. You will never need to do this. This is just something that justifies our equations and the stuff that we are going to do in the future. So pay attention because it's actually kind of cool. Okay, so integral from 0 to y, and my force vector is going to be fg vector. And then my dr, since it's just in the y direction, I'm just going to call it dy. Then, if I plug in, or if I think about my force of gravity, the vector force of gravity, that's going to be equal to mg comma 0. And my dy vector, that's going to be just equal to, so vectors, that's going to be equal to 0 comma dy. Oh, and I screwed up. I messed that up. There we go. All right, so force of gravity vector is 0 comma mg, not mg comma 0. Now, when I do this dot product, it says take 0 times 0 and take mg times dy. So what I get is my integral from 0 to y of force of gravity, which is mg y hat, dotted into dy y hat. Still integrating from 0 to y. I'll have m times g times dy, and then I have y hat dotted into y hat, but that is just 1. And I take the integral from 0 to y of mg dy. And this is the integral that we're going to do. And so my m and g, those are constants. So just like with differentiation in integration, we can pull constants out, and I get the integral from 0 to y dy. I'm going to give this y maybe a dash, a prime, because we're not actually going to be, because we have our y up here without a dash. I'm going to put a dash on this y just to make sure that we understand these are different things altogether. So my integral becomes integral, or mg times the integral of dy prime. So my mg stays the same. My power rule for integration says if I have something, integral of x to the n dx is equal to 1 over n plus 1 times x to the n plus 1. I could think about my integral. As being maybe not mg integral dy. Think about it as an integral from 0 to y of y to the 0th power times dy, and these are y primes. So my formula says when I do this integration, I will take 1 over, so n here is 0, and it says take 1 over n plus 1 times y to the n plus 1, so 0 plus 1. And then evaluate it at your limits of integration, 0 and y. So this is 1 over 1, and that's just 1. And then we have y to the first power, which we'll just call y prime actually. So I get mgy prime evaluated at the points 0 and y. That is equal to mgy minus mg times 0, which is the whole thing goes away, and I'm left with this mgy. And this is the work that is done by the force of gravity. So let's talk about another example where we'll do the work done by a spring force. So here's my situation. I have a spring, it's attached to a wall. I have it stretched out some distance, and I'm going to start at X and go, it's going to pull back and cause us to go to 0. I'll say that my positive X is in this direction. And so if I think about my force, it's going to be pointing this way. So my spring force, F spring, is to the left in the negative X direction, and my displacement will also be in the negative X direction. So my work integral says work is equal to the integral from a to b of force vector dotted into dr vector. Now our force vector, F, is going to be the spring force, comma 0. So there's all of our forces in the x direction, and it's that spring force. My displacement vector, dr, I'm going to just call that dx, comma dy. And this is something that you can do when you're integrating Cartesian coordinates. Your dr, your 3-dimensional or 2-dimensional thing that happens on a path integral, your dr, can be split up into its x component and its y component like this. So when I do this dot product, f vector dotted into dr vector, what I get is, we'll say, do the other notation, what I get is f spring times dx, and then there's an x hat dotted into x hat because this spring, f spring, has an x hat, and this dx also has an x hat with it. And then plus 0 dotted into, or 0 times dy times y hat dotted into y hat. So those x dot x and y dot y things, those are both 1, but on the y component, it's 0 times all of that, so that whole thing just goes to 0. And what I'm left with then is just the spring force dx. My spring force, I know that that is minus k times x, and then that dx stays right there. So my work integral, I'm going to change it around. I'm going to say that we're going to start at x and go to position 0. And then my force is going to be, the f dot dr thing is going to just be that minus kx times dx. I'm going to call these x primes because we're integrating over these x's. And so I don't want to confuse them with this x here, which is going to be a part of our result. So my integral, you can see it's starting off, it's usually that we start off at 0 and we integrate to x. And so anytime I'm doing a path integral, I can always flip the order of my limits of integration, and I can do that at the cost of a negative sign. So what would happen is that this integral up here is equal to the negative of the integral from 0 to x of k times x prime times dx prime. And that was negative as well, so those two negatives will cancel out. So I get the integral from 0 to x of k times x prime times dx. K is a constant, so it just comes right out front, comes out of the integration. So I get k times the integral from 0 to x of k times x prime times dx prime. Just like before, our integration tells us that the integral of x to the n dx is equal to 1 over n plus 1 times x to the n plus 1. Here we have just k times x, so that's x to the first power, which means n is 1. When I apply that formula to it, I get k times 1 over 1 plus 1 times x prime to the 1 plus 1, and that will be evaluated at 0 and x. So 1 plus 1 is 2 down here, and I get 1/2 k times x to the power of, or x prime to the power of 1 plus 1, which is squared. And we're still evaluating at the limits of 0 and x. So now I'll plug in those limits, and you can see the x prime goes away, it becomes an x. I get 1/2 k x squared minus 1/2 k 0 squared, and that whole term goes away. And what I'm left with is this equation that says 1/2 kx squared is the work done by a spring force. So this is an important thing as well. We'll see it pop up again when we talk about energy, especially different types of energy like the potential energies. And yeah, that's pretty much it. So I'll leave you with one more practice problem that we can do for this video. Let's say that I have a force, and it's a friction force. So I've got this object up to speed. It's on a horizontal surface. It's moving with some velocity v, and there is friction. So my free body diagram will be my normal force, my force of gravity up and down, and then I'll have a friction force pointed in the negative direction. We'll say this is to the right is positive x, and to the up is positive y. And then I can ask about, like, let's say that this thing moves for a total distance of 3 meters before coming to a stop. And I know my friction coefficient on for that surface is something like, say, 0.5. And the mass of this box is 100 grams, or 0.100 kilograms. The question is, how much work will friction do as it slows this thing down to a stop? I'll give you a moment to try to work it out for yourself, and then we'll come back and give it a shot. Okay, hopefully you've gotten it figured out. If not, we'll go through it right now. There are two ways I can do this. I can think of this as work is equal to the integral of force times distance, or force times displacement, and we go from 0 to 3 meters. My force vector, let's not do that, is friction. And that would be equal to mu k times my normal force. But if you look at our free body diagram up here, it shows that our normal force is equal to the force of gravity. So I get mu k times n, which is equal to mu k times m times g. And this is going to be entirely in the y hat. Or sorry, not the y hat, in the x hat. And it'll also be in the negative x hat. And it turns out that my limits of integration, I've done them incorrectly, because I'm going to start at 3, and I'm going to go to 0. So my integral for work is going to be the integral from 3 to 0 of friction force dotted into displacement, dr. But dr vector, we already said that just dx or maybe I'll back out of that. We'll call it dx in the x hat plus dy y hat. And I'm going to integrate between my starting position of 3 meters till my ending position of 0 meters. And the integral is going to be f dot dr. So I'd have my mu k times mg in the negative x hat direction plus 0 in the y hat direction. And we dot that vector into dx x hat plus dy y hat. Oops, sorry about that. All right, so when I do this dot product, my integration limits stay the same. Integral from 3 to 0, I get a negative mu k mg times dx times x hat dotted into x hat plus 0 times dy times y hat dotted into y hat. Second term is going to go to 0 because of that 0 force, 0 friction force in the y direction. And so I'm left with then is the integral from 3 to 0 of negative mu k times m times g times dx. Again, this x hat dotted into x hat, that just becomes the scalar 1. And what I have now is just a regular old integral that we've probably seen something similar to this before. So again, I will flip the order of my limits of integration to make it a negative integral from 0 to 3 of negative mu k mg dx. The negative signs will cancel. Negative 1 times negative 1 is positive 1. And I get the integral from 0 to 3 of mu k mg dx. From there, I would just go about pulling out my friction, or my constants. My constants are mu k, m, and g. And I get the integral from 0 to 3 of dx. So that would be mu k times m times g times the integral from 0 to 3. I'm going to call this x to the 0th power because just like 1 times dx and x to the 0 is 1. So we get x to the 0 times dx. Our rules of integration tell us that the constants are unaffected, but then my x to the 0 becomes 1 over 0 plus 1. Again, our n here is 0. 1 over 0 plus 1 times x to the 1. And then we evaluate that at the position 0 and 3. So my mu k, m, and g stay the same. I get 1 over 0 plus 1, and that is just 1. And then I get x to the first power, and we evaluate that at 0 and 3. So mu k is known to us. It's 0.5. The mass of the object is 0.1 kilograms. G is still 10 meters per second squared. And then we have x evaluated at 3 and 0. And these are units of meters because it's x. If I plug that stuff into my calculator, I would get 1.5. Well, 1.5 kilograms times meters over second squared times meters minus 0, and the units will be the same for that. So the answer would be just 1.5 joules. So the the friction force as it slides to stop, this 100 gram mass slides to stop, it will be 1.5 joules of work total done by friction. So one more thing that I want to get at, and just so that we're clear, you saw in these previous two examples that we had these negative things and it became a positive integral because we flipped the order of our limits of integration. This is because work is a scalar. It'll always come out to be a positive. Work does not have a direction to it. There's no work in the x-axis. There's no work along the y-axis. It's just work. Sometimes we can have a negative work. If work is negative, this will be like slowing something down. So friction or your brakes, they slow down your car, or it slows down this block in the last example. Slowing down is due to a negative work. But if I wanted to push on it and cause it to go faster, that 100 gram mass, or if I hit the gas pedal and then the engine revs up a little bit and causes more force to be delivered to your car's wheels, that would increase the speed. And so when we do positive work, we're speeding up. And the direction really doesn't have, or this negative sign, negative work, doesn't have anything to do with what direction it's pointed in. It has to do with whether or not we're taking we're taking stuff out, like taking velocity out of our car, or we're adding velocity to our car. Right, so work being positive or negative doesn't really mean that it's a direction thing. It just means whether we're adding or removing velocity to our car. The other thing I want to say is that when we use this equation, work is equal to F times D times cosine theta, this F here is a magnitude, or another way of saying that is an absolute value. Same thing for the displacement. This is the absolute value of the displacement. So when I use this equation, FD cosine theta, make sure that you plug in a positive force and a positive displacement, and you will get a positive number out. But like I said, work can sometimes be negative for sure, like we can slow down a car. And if my car was slowing down due to friction, that's because my friction points this way and to the left in the negative direction, and my velocity or displacement will point to the right. And so the angle between them is 180 degrees, and this cosine is what gives us a negative. You never, ever, ever get a negative from your force or your displacement when you do work equations. You always get your negative. The only place that your work value can become negative is due to that angle between the force and the displacement vector. When you use F is equal, or work is equal to FD cosine theta makes things negative or positive, but never force and never displacement. Always use the absolute value when you plug those into this equation here. So, all right, with that said, I'm going to go ahead and stop this video. I'll come back with a energy video, and we'll go from there. So, hope this was useful, and we will see you later.